Edexcel Core Pure, complex numbers 5, complex roots. The nth root of any complex number. So now we're going to consider the situation where z to the n equals w. So previously we've looked at z to the n equals 1, now it's z to the n equals w, where w is a known complex number. So z is going to be referred to as r cos theta plus I sin theta, and that is the thing we're trying to find. And w will be referred to as s cos phi plus I sin phi, and that is the complex number which is known. So we're going to use a similar approach to when we looked at roots of unity, except we need to know the modulus and argument of w before we can start a problem like this. So if z to the n equals w, and we already have that in polar form, as we can see, then we can express this as r cos theta plus I sin theta to the power n equals the complex number called w. And don't forget, as we're going through this, that w is a known complex number. So we'll know s and we will know the value of phi. If we now apply the Modulus Theorem, we get r to the n cos n theta plus I sin n theta equals s cos phi plus I sin phi. So at this stage, if we look at the modulus, we can see that r to the n equals s, and indeed r, the thing we're looking for, must be the nth root of s. Also, if we look at the argument of each side, we can see that n theta equals phi. However, in order to get all n roots of w, we can't just consider phi, we need to consider phi plus multiples of 2 pi. So we look at a 2k pi, which means that theta, which is again the thing we're looking for, is phi plus 2k pi over n. So to summarize, we're trying to solve z to the n equals w. Z is unknown, so it's r and theta that we're trying to find. W is s cos phi plus I sin phi, and we know the values of s and phi, they're given. And once we raise z to the power n, then we can use the Modulus Theorem, and we can then look at the modulus of both sides to get r is the nth root of s, and we can look at the argument of both sides to get theta is phi plus 2k pi over n. You're going from 0 up to n minus 1. And it's worth noting, just for the record, what happens when k does equal n? What happens if we go a step further? Then theta would be phi plus 2n pi over n, which is phi over n plus 2 pi. So that 2 pi is one complete extra revolution, which is the same as phi over n, which is exactly what we would have got if k was 0. So to summarize, the nth root of s is r, which is the modulus of z that we're looking for, and this argument here is theta, which is the argument of z, which again we are looking for. So here we want to find the cubed root of minus 1 plus root 3i. So the first thing we've got to do is to set up the problem. So if we're looking for the cubed roots of this, then z cubed must give me minus 1 plus root 3i, and this complex number is the thing that we've previously been referring to as W. So we need the modulus of W, which after a bit of Pythag is 2, and that's the thing we've called little s. And we need the argument of W, which is 2 pi by 3, and that's the thing we've been calling phi in our introduction. So we can now say that z cubed can be written as 2 cos 2 pi by 3 plus I sine 2 pi by 3. So now we're in a position to take the cubed root of both sides in order to find z, which is the thing that we're looking for, which will give us a cubed root of 2 cos, and before we can apply Modulus Theorem on this side, we need to add on a multiple of 2 pi before we apply the power of third, and likewise this one will be the same. 2 pi by 3 plus a multiple of 2 pi over 3. And we need to add on that 2k pi to both arguments in order to make sure we get all 3 cubed roots. So now we know that r, which is the modulus of our answer, is the cubed root of 2, and theta, which is the argument of our 3 answers, will be 2 pi by 3 plus 2k pi over 3, where k is 0, 1 or 2. So all three roots, all 3 answers will have r equals the cubed root of 2 as their modulus, but the arguments will differ. So when k is 0, we get theta is 2 pi by 9. That's the argument of one of the answers, or one of the roots. When k is 1, we get theta is 8 pi by 9 as the principal argument. So that's the argument of our second root. And when k is 2, we get theta is 14 pi by 9, which, notice, at the moment hasn't been converted into a principal argument. But these are 3 arguments for our 3 cubed roots of -1 plus root 3i. So to summarise the method, we found the modulus of w, which we've called s. We found the argument of w, which we've called phi. And when we applied the Modulus Theorem, we added on that extra 2k pi to make sure we got all 3 cubed roots of w, and r was the cubed root of 2. So by letting k equals 0, we got that argument. When k is 1, we got that one, and when k is 2, we got that one. And we can look at these roots and other roots of complex numbers using a Geogebra file. So this diagram is showing z cubed equals -1 plus the square root of 3. This is the closest I can get to the square root of 3, so the diagram isn't absolutely exact. At the moment we are looking at the first of those 3 cubed roots. So there's w. So this is the complex number we're doing cubed roots of, and we can see the first of those roots shown on the diagram. And as I go to the second root, we can see the modulus and the argument, and as I go to the third root, we can see the modulus and the argument. And these are matching the 3 roots that we found on our method. If I now go to, for example, the 4th roots of w, we can see that they form a square. And if I go to the 5th roots of w, they form a regular pentagon. And as I go through the different roots, there's the second root, the third root, the 4th root, the 5th root, and back to the first root. And look what happens when we move w around. So when we move w, we can give it a bigger modulus, and we can see all 5 5th roots on our eigen diagram. So if we go to the fourth roots of W, again we can see what happens as we move W around. In the next video we're going to be looking at solving equations.